Today's goal is to solve rational equations algebraically. Solve, of course, means find the solution, or the values that you can substitute into the equation to make the equation true. We'll be dealing with rational equations, and working algebraically means, again, we're not working graphically. Example 1. Use the example below to describe the process of solving a rational equation algebraically. Oh, this is nice. This is like looking at a textbook and seeing an example with all the steps already laid out, and we just have to analyze like how are they getting from step 1 to step 2 and so on. So let's take a look at step 1. They're just recopying the equation. In step 2, step 2 looks like they're recopying the equation. They're just factoring the denominator of the rational expression to the right. So they're just factoring denominators. There's nothing to factor in the denominators here and here. They're already factored. Let's take a look at step 3. What's new in step 3? Well, this appears to be new, and this appears to be new. How are they getting these things? Oh, I can see in step 4, now we have a common denominator. So step 2 must be multiplying to obtain or to get a common denominator. So in step 2, they factored to choose a common denominator, and now it looks like in step 3, they're actually getting that common denominator. Notice that when we're figuring these out, we're sort of moving backwards and forwards. It's okay if you don't look at a step and immediately know. Do take your time. Okay, in step 4, we have a common denominator. How are they getting these? Oh, it appears they distributed the 2x to both of these terms, and they distributed the 1 here. And then they went ahead and added, since at this point you do have a common denominator. Okay, in step, look at step 5. There's no longer a denominator. Oh, well, we can see in step 4 they have the same denominator. This would be like saying if 2 over x if 2 over 7 equals x over 7. Well, x is obviously 2, right? If you have the same denominator, then the numerators must also be equal. So once the denominators are equal, then you can just set the numerators equal to each other. That's what's happening in line 5. And then at line 5, at this point, you just turned a rational equation from step 4 into a quadratic equation. And we know how to solve quadratic equations. In line 6, we see they're just getting all the terms on one side of the equation. And then line 7, they start to factor by grouping. Now, of course, if you're using the guess and check method, you could jump straight from line 6 to line 9. You're just factoring. Or if you're not comfortable factoring, you could use the quadratic formula. It takes more time, so I strongly suggest that you get comfortable factoring. But they're just solving the resulting equation, which just happened to be quadratic in this case. And then in line 10, they're setting each factor equal to 0. 11, they're getting the answers. Now in line 12, this is interesting. We see the original equation is undefined for these two x values. And one of these x values is an x value that we got. So what they're saying is 3 can't possibly be a solution. 3 won't make the original equation true because, for example, if you substituted a 3 in the original equation, you end up with 1 divided by 0, and 1 divided by 0 is undefined. So 3 cannot possibly be a solution. Therefore, we cross it off. It's called an extraneous solution. Inside the word extraneous, do you see the word extra? So an extraneous solution is a value that appears to make the equation true, but does not actually satisfy the equation, right? 3 came up, it looked like it was going to work, but we had to be really careful to double check against our discontinuities. Okay, let's follow this general process onto the next one. Here's our next rational equation. So looking back, we see the first thing we needed to do was get a common denominator. Factoring is the tool that allowed us to choose, but in this case, we can just see 6 is 2 times 3, and 2a is just 2 times a, 3a is 3 times a. So we can see right away our least common denominator is going to need a 2, a 3, and an a. So let's fill in with what's missing. I like this sort of bracket notation because it helps us see what are the new things you're multiplying in, what are the pieces or the rational expressions that came from your original problem. So, for example, 1 over 6, it's got the 2, it's got the 3 in the denominator, you just need the a. And here we've got the 2 and the a, so we just need to multiply by 3 and multiply by 2. Okay, now let's get our common denominator. We'll distribute here. Again, we'll distribute here. Now that we have a common denominator, if the denominator is the same, the numerator must be the same. So we have a equals, if you wanted to break this into 2 steps, you can. A would equal 3a plus 4 plus 2a plus negative 6. You're distributing the addition sign in this case all over 6a. And now the denominators are the same, so the numerators must be the same. So we have a equals 3a plus 4 plus 2a minus 6. Now in our example, once we dropped the denominators, we ended up with a quadratic equation, right? In line 6, you see that x squared. We solve quadratic equations by getting everything on one side. You wanted it equal to 0 and then factoring. But this is not a quadratic equation. We turned a rational equation given to us into, this is just a linear equation, right? There's no a squared or a cubed or anything like that. So we'll combine all our like terms. And then we want the a's on one side instead of everything on one side. And then we have a is 1/2. Oops. I think I made a mistake somewhere. Did you catch it? I hope that you did. Sorry about that error. 3a plus 12. And then when we combined 12 with negative 6, we got positive 6 here. Sorry about that. I hope you caught that. And so a is negative 3/2. Now, when you're solving normal equations, you would box it in and be done. But remember in the first example, you have to go back and check if this is an extraneous solution, an extra value that appears to work but doesn't really work. Well, you're checking it by seeing what are the discontinuities. If we look at our original equation, we can see that a cannot be 0. That's the only number that would make my denominator equal to 0. So 0 is the only value a couldn't be, so negative 3/2 would be totally fine.